Okay, so Monica will give the last talk in the lecture series.
Thanks for staying with me to the bitter end. I've been less sleepy than yesterday, so hopefully I'll be more coherent and less scattered. So a few odds and ends to tidy up is we have this trivial item post. In the finite Hecke algebra, and I didn't actually write out a formula for it. That's an exercise for you to do. Start with H2. And if you, of course, it sits inside the DAHA. If you take sort of this corner ring, sandwiching it between the idempotency, the identity of this ring will be E plus. This is the spherical DAHA that came up. That phrase came up before. So, but I think I wasn't sure if I had ever spelled out what it was. So that's the spherical DAHA. And as we heard, there's connections, at least when you take your Q and T and specialize them appropriately to elliptical. And then, right, as we saw, again, if you again take this trivial idempotent and apply it to the polynomial representation, this is where symmetric Macdonald polynomials live. And then also connected to this, or to the DAHA, I didn't say this before. So with the Hecke algebra and affine Hecke algebra, we sort of drew our pictures, and then we said, oh, put it on a cylinder. And I haven't drawn pictures for the DAHA. And what would you want to do there? Well, would you want to put it on a torus, right? If the x's are winding this way, then the y should wind that way. And I'm not going to draw any of those pictures or make anything precise because I think there's still it's still a bit murky in the field about whether you can draw those staining pictures and really get the DAHA or not. How do you have to specialize Q and T? You have to throw in some little extra defect. Like, you know, the relations between the x's and y's to get them to be correct. You have to do some trickinesses there and knowing things don't collect. So I'm not going to draw those pictures, but being able to draw those pictures on a torus, you should think about that, and it's probably going to come up in a few of the talks next week. And then, of course, any talk that says DAHA in the title, hopefully you'll go to those, or you'll get something. Something in this week would have prepared you, hopefully, for those, but maybe not. Who knows? Okay.
Yeah. Maybe to just what you're saying is, in other words, is that in the same way that the affine Hecke algebra is a quotient of the affine braid group, that the double affine Hecke algebra is a some kind of quotient of the torus, or the braid group of a torus by some quadratic relation.
Mm-hmm.
Like a deformation of the braid group of torus, like a q-deformation.
That's what she's saying. You can put a, you can take a single mark.
Yeah.
Take a single
You
mark.
have to do some kind of Q defect, tweaking it, do something to get it to work. Whereas for just the AHA in the cylinder, it looks great. And then another thing I want to say, talking about the polynomial representation. Well, the way we built it, if you want to know how a y acts on it, you can just compute it. Or you could say, is there a formula like we have for the RCA Dunkel operator? And yes, you can write down explicitly what those are. And I didn't do my homework and get the formula and write it down for you, but it's just a formula. But you can. It's some kind of differential operator that has some permutation part to it, too. So you can, whoops, can you? You can. Or I guess I should say, you might want to take maybe actual polynomials versus Laurent polynomials when you're talking about that action. And so they're like, oh, I think we should also call them Dunkel operators. All right, so. Oh, and let me just remind you the way that we were writing this polynomial representation was, as a vector space, it's Laurent polynomials in the x's, but how do you get the action? We were taking the affine Hecke algebra on the y's, inducing up to the DAHA of a one-dimensional representation. And that one-dimensional representation, it was trivial, so that means the big TI's act as the scalar t, and the yi's also act as scalars, powers of t, I can write it explicitly, twice I minus 1. So y minus t squared to the I minus 1, acting on this trivial guy is 0. And again, as a vector space, polynomials in X. Okay. So I think that, despite various notes I've written to talk about various things, for the time that we have left, I'm going to end up mostly focusing on this representation today. Okay. So, opposition for Q and T generic, and we'll see more explicitly what that means as we go. This polynomial representation of the DAHA is irreducible. And it has a y weight basis that we can construct. Okay, and we're mostly going to see how one might prove this by getting our hands dirty with it. All right, so to do this, let me recall from yesterday, we had this equation that I was calling star 1. I'm just going to call it star today, and I'm going to take the y version of it instead of the x version. So I used lowercase f before, so I'll use capital F now. Just use curly y for the Laurent polynomials in the y's. So if you want to move a polynomial within y's past the t, the relation is TIF minus f, where you swap all the yi's and yi plus 1. Ti is little t minus little t inverse times, on the numerator, f minus f permuted by si. And the denominator, 1 minus, well, now it's going to be yi on yi plus 1. What is the polynomial x's? We just had xi and xi plus 1. Okay. And let me make a remark about this. This yi over yi plus 1 that we're seeing in this denominator, again, so we said it divides it because we're doing f minus si, so it's an honest polynomial there. But if we just look at this, we could think of this as y sort of to the epsilon I minus epsilon I plus 1, thinking about weights for GLN, right? And if we're thinking of GLN or, blurring distinction with SLN maybe, we can think of this as y alpha I, where alpha I is a simple root. Okay? And maybe what I really need to be careful would maybe be an alpha I check there, except the joy of working with type A and GLN, you can be really sloppy with alphas and alpha checks. So I never remember what it actually is. I didn't look it up. Okay, and then the other thing is nut. And what's alpha nut? Well, on the other hand, by my trick, y0 is just cubed yn over y1. And then you match this and you say q is y to the delta. And that's what's really happening with this q. So this question came up before about what's the difference between q and t. Very different, right? T is my quadratic parameter. Q is like my imaginary root. And so when you build the DAHA not just in type A, but in other types, this is giving you a sense of how it might be defined. That your subalgebra that you're talking about is really going to be, say, you know, the group algebra of your weight lattice. Or maybe root lattice, or maybe some lattice in between. And how do you get the relations and what's going on with these parameters? They have to do with understanding affine root systems and understanding how the appropriate affine biology acts there. So now you're set to go do every other type. So you can define your DAHA for other root systems, but again, it's more than just a root system because you have to say, what are you doing for the x's and what are you doing for the y's? And they don't have to be exactly the same. Like even in type A, you could do like, you know, an SL weight lattice for the y's and, you know, a PGL weight lattice for the x's. Or I've done GL. Yeah.
In other type, what is the analog of this picture that you said with the great group of decodes?
No.
There is for C-check C DAHA, there's a beautiful picture of the orbital Bray group. I don't know for type P. I think Katrina Stockholm does.
All right, so let's keep studying this polynomial representation of the DAHA. And thinking of it as polynomials, of course, we use our second presentation. But if we want to calculate and compute and do things, it turns out using our first presentation makes life a lot easier. So let's flip back to our first presentation. All right, well, then this has a nice basis. And next, by think of what your PBW basis looked like for the DAHA. Instead of saying x's and finite Hecke and y's, we had affine Hecke and y's. Right? So let's use that. So via my first presentation, that means that a basis that we can take of this polynomial representation is TW tends to 1 for W in what? So if I put all of affine Sn here, and I had y's, well, that would give me the whole DAHA, but I'm not inducing just from the y's, I'm inducing from this AHA on the y's, meaning I've gotten all of my y's, but I've also killed on the one side my finite Hecke. So we have to take cosets, affine Hecke and finite Hecke on the correct side. And that'll give you the right size. All right. So when we look at this, I'm going to convince you that my yi's act triangularly on this basis. Okay. I could have instead said, you know, take basis of monomials here and y's acting triangularly there, but figuring out the action and convincing of you that of how the y's act would be difficult. Whereas here it's going to be quite easy. And triangular with respect to one order. What order? For, you know, some nice order defining length. Length on your affine symmetric. So, right, so if we have an F moving past a TW, space, so that's going to be what? TW, F acted on by W, plus lower order terms, much like in Gregor's talk when he was where the Cherednik polynomials came in. It's like to be low order terms, right? And then you said, you know, you could figure out and get a weight basis out of that. And so, of course, this is also true if I stick tensor 1 in there. And again, lower order with respect to how I've ordered my affine symmetric group defining length. Okay? And why is that true? It's true because of star. Right? When an F. Okay, well, this relation works whether it's to the right or left to right. Maybe I wrote it differently from how I wanted, but right, an F moves past the T and it gets permuted around, and notice there's no T's on this side, so it's going to be smaller in length as I have many, many, many T's making up my TW. And so all we need to do then is figure out for my Y's what new weight I'm getting, and then not worry about the lower order terms if I want to understand the spectrum of my Y's on this whole basis. So I don't have to diagonalize what I want to say. If you can write your Y's as upper triangular matrices, and then if you've got distinct weights, you've got distinct things on the diagonal, you know you can diagonalize them. And you know that basis is out there even if you don't actually go and find that basis. So let's do that. So let's see. This says the Y's are acting as upper triangular matrices. Or lower triangular. I don't know. It depends on how you order your lower order terms. And so if we can say that those weights are distinct, then it will say we can diagonalize them and you don't have to explicitly do it. We can explicitly do it, but we don't have to. All right. So let's get our hands really dirty. Let's take n equals 3. Okay. So I've got sort of, you know, so one tensor 1 sitting inside of there. And how are y1, y2, and y3 acting on it? I erased it, but my trivial representation, all the big T's act as little t's. I'm showing that the y's act as these increasing powers of little t. Right? So that's, here's one of my weight vectors inside of there. And notice that, well, what if I said, you know, let's look at T1 tensor 1 and figure out what the y's are doing there. Well, then you'd say, no, no, no. Recall that I'm tensoring over my affine Hecke algebra, and you're just scaling things. You're not getting anything new and linearly independent. Well, that's okay, because I never said my basis was everything in the T's, only my minimal length coset representative. And so I don't need to consider T1, I need to consider something like T0 or pi. So let's consider those. Oh, and before I consider that, let me notice, so, right, you don't consider a T1, it's not a middle length coset representative. Combinatorially, why are we seeing that, or what's happening is, right, so T1 is wanting to swap that 1 and that T squared, and it turns out those are illegal moves. That if two neighbors differ by a T squared, those end up being illegal moves. And you should kind of think to yourself, it's kind of like the structure of standard Young tableau, when you're looking at the symmetric group. If you have a 1 next to a 2 or 3 next to a 4, whatever, you can't swap them. Whereas if the 1 and the 2 are existing somewhere else in a standard Young tableau, you can swap them. That's the same thing that's going on here. Okay. So let me write that. So the idea is that if you have sort of two neighbors in this tuple of how the y's are acting, right, I'm calling this, say, b1, b2, b3, if you have bi plus 1 over bi, that quotient being t squared, then we're not allowed to commute them. that's capturing some of this minimal length cosine stuff. Okay. So, all right. Let's look at pi tensor 1. Okay. And let's see how y1 and y2 and y3 are acting on that. Okay. Well, let's do my trick of thinking that we don't just have y1, y2, y3, we have yi for all integers. Okay. And then remember that, right. So remember that y0 is like qy3. And so that means that there's sort of a qt to the fourth sitting out here, and a qt squared sitting out here, and there's a q inverse here, and a q inverse t squared there, and so on and so forth. We have these q shifts as we wrap around. Okay? And so now if I want to act by pi, pi just shifts my window. Okay? So I'm going to have qt to the fourth, 1 t squared. Take that window there. Because remember, conjugating a y1 by a pi moves it to a y2. All right. And so, and we also have something like T naught tensor 1. And T naught is a minimal length cosine representative, so that's valid to look at. And what am I going to get? I'm going to get q t to the fourth, t squared, q inverse y, because S0 just swaps 0 and 1. So we're just swapping this red qt to the fourth with this 1, but you have to do it 3 periodically. So the q inverse and the t to the fourth also swap. And so part of what's happened is we've kind of upgraded our action. So remember when we had the affine symmetric group acting on R to the n, that we used to say that S naught sends a tuple A1 up through AN to, you do up here AN plus 1, dot, 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 A1 minus 1, and everything else in between stayed the same. So now when we're talking about sort of the affine symmetric group acting on our space of Y weights, we're actually saying that S naught, so let me call them B1 up through Bn instead of A1 up through An, right? Instead, you're having Q e to the n here, and Q inverse B1 here. And likewise with pi, right? You're getting a Q in there as opposed to a something plus 1. B1 up to Bn, B1, B2, Bn minus 1. Okay, so it's the Q version of our old action. Let's do one more of this and then we'll step back and see what we've learned. Let's do actually let's do 2 more. So if we have T1, T0, 1, I claim that's going to correspond to t squared qt to the fourth q inverse, right? Now you do get to commute the first 2 entries. Their quotient isn't a t squared. And let's jump all the way to T1, T2, T1, T naught. tensor 1. I claim that is also a minimal length coset representative. And there we've got q inverse t squared qt to the 4th. Okay. And recall, back when before we got to Hecke, when we were just talking about symmetric group, that S1, S2, S1, S0 inside of affine S3 is a translation. Right? We saw it was a translation basically by minus 1, 0, 1, which would have meant in the A coordinates, you would have kept the same order A1, A2, A3, but you would have subtracted 1, added 0, added 1 there. And what's happened here, we Q-ified it. So we took our original 1 t squared q to the 4th, and we decorated it with powers of q, according to that translation. Put a q inverse here, a q to the 0, a q to the 1 here, but keep that underlying 1 t squared t to the 4th. Okay, so we have these translations. And so basically, if you were to act on our original weight vector with weight y weight 1 t squared t to the 4th, and if you were to act by the entire affine symmetric group, not just the minimal and coset representatives, what are you going to get? You're going to get all the ways of plunking powers of q on here in any way you want. Those are your translations. And having done that, then you can permute the entries. And if there's no relations between q and t, and if nothing's a root of unity, you can see that those are all distinct from each other. Right? So, note all of these, q to the, say, q to the lambda 1, q to the lambda 2, t squared, q to the lambda 3, t to the 4th, and all sort of S3 orbits of these. They're distinct if q is never equal to 2 squared. Let's see, if you have a q to the a, never has the form t squared to the b, for a, b being integers except for 0. And if q and t are not roots of unity. So these are the conditions to make these all distinct. And these are my genericity conditions, basically. Okay. So we get, and that's even taking all of the affine symmetric group, not even the minimal like coset representatives. So now, if we want the actual y weights that occur, then we can just understand, in terms of doing these translations and permutations, which ones are the minimal like coset representatives, and that will tell us which subset of these that will cut out. Or you can figure it out by doing the Mackey formula. Right? We have an induced module, and basically saying restrict it back down to the y's, understand those double coset representatives, and twist by those. And because you start with the one-dimensional, you don't need to do that anything funny with the restricting. It all comes in the twisting action. Okay. But in the interest of time, I won't actually write it out in terms of Mackey and those double coset representatives. I had originally intended to, but you can actually see it here explicitly and just keep track of it on your own. And what time am I ending? I forgot what time I started. At 12, what? 50. Yep. Okay, oh, I still have half an hour. Yippee. Okay. So now you should believe me that I can find a y weight basis, that all my weight spaces are one-dimensional. So all my y weight spaces are one-dimensional. All of those weights are distinct. In other words, yes, I got an upper triangular matrix with distinct weights. Well, across the family, right, distinct weights. Okay. So how do I find that eigenbase? So now I know that weight basis exists. How do I find it? Right? So we have a y weight basis. What if you wanted to find it? Of course, in some sense, we don't have to. So, but I think it's a beautiful part of the theory of the representation theory of even already the affine Hecke algebra.
So in particular, that you're asking, how do you get the formula for this non-symmetric Macdonald polynomial? Is that right?
Correct, thank you. This y weight basis is up to rescaling are the non-symmetric Macdonald polynomials. And if you wanted to write an explicit formula for it or go and compute them, this is, yeah, how would you actually go and compute it using this machinery? Okay, I'm going to use these things called intertwiners. So before I write a formula for them, let me tell you the properties that they have. That's really nice. And if you wanted to, once I told you these properties, you could do some calculations and just find them on your own. And you might find a slightly different normalization, but you could go and find them. So, in fact, so there exists these operators, I'm going to call them phi sub I, in your double affine Hecke algebra. And in fact, this is already true on the level of the affine Hecke algebra. Let's do the affine Hecke algebras in our Y's. If I is only running between 1 and n, but you can also allow I to be 0 here as well. Okay, so I have these new operators sitting inside of here, such that if I take some polynomial in the Y's, and I want to move it past a phi, right? So far this looks like star, right? If I had a ti there, and then I would have plus blah, 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 which would be a lower order term with respect to length. Well, that's it. You're just done. Okay? It honestly moves past by permuting it, as though you were living in the semi-direct product of polynomials with the affine symmetric group. Okay? So if this is true, that means that these operators are going to send y weight vectors to y weight vectors. But they could kill them, right? You want to make sure that you don't just get 0, because 0 is a weight vector. Okay, so what else is happening? So another property that they have is 2, so you can choose them such that they satisfy the grade relation. Okay. So that means that phi w makes sense. Now I said you can choose them, meaning, you know, there's some normalization, etc., that's not necessarily agreed upon. Notice that because polynomials and y's commute with each other, if you were to take phi and say right multiply it by some nice fixed polynomials and y's, this formula would still hold. And so various authors will choose to rescale these by various polynomials and y's to get slightly different families. You'll still have this property. If you choose them wisely, you'll still have the grade relations holding. Okay. Right. Let me, I'm one by one unfolding the properties. And also, certainly we should set phi sub pi to just be pi, because we already saw that pi has the intertwining property that we want. And so what that means is that up to rescaling, that means that our non-symmetric Macdonald polynomials can be found among this list, right? So we have one. Okay, we have one, but we should think of one as corresponding to the element 1 tensor 1 in my representation. Right? So you can have things like phi0 tensor 1, phi1 phi0 tensor 1, right? phi2 phi0 tensor 1, blah blah blah, phi1 phi2 phi2, phi1 1 2 1 0, and so on and so forth. And don't forget pi tensor 1, pi 0, etc. Right, so minimal length coset representatives without pi's, with degree 1 in pi's, degree 2 in pi's, and so on. Okay. Also pi inverse going in this way, and so on and so forth. Now, if you want, when you go back to the other presentation with x's instead of t0s and pi's, right, we know how to do that. If you want to pick out honest polynomials in here, there's some kind of line you have to draw, not line, some kind of path that cuts them out. But as we saw, if you do enough powers of pi, right, you can always clear denominators and get your honest polynomial. So if you want to avoid the Laurent region, you just go low enough, and of course, right, this one is just x1, x2, x3 tensor 1 when we go back to presentation 2. Okay? And we'll calculate some of these in a few minutes if you have patience for that.
So you're saying that these properties imply that these elements are eigenvectors for you?
Yes, yes. Once you know they have the intertwining property, that means that, you know, how does y act on this? It moves through, it gets acted on by S1, S0, and it acts, so this is going to be a weight vector. Now, what I would like, if I had t's here instead of phi's, this would be building up a basis. I want it to still be a basis when I put phi's there instead of t's. So I should tell you a little bit more about the phi's to convince you it really is a basis.
But it's not true that anything satisfying the properties on the second two-board will be the basis, right? You take all the phi's.
Correct, correct. For instance, if you write multiplied by some polynomial in y's that vanish on something, then you're going to kill something away. Yep. And again, these intertwiners are really wonderful tools that you can use more widely than just here. I use them all the time. Okay.
And in particular, these hold inside the algebra, so they work on other representations too.
Yes. Yeah, good comment. Yeah. So this is true in the algebra. We're only sticking the tensor 1 on later to apply this particular representation. So, all right. So, well, let me just tell you the PIs that I like to pick have the following formula: TI, YI minus YI TI. Just a commutator of a T and a Y. Now, why is that my favorite formula for it? It's a commutator. You can write it down. And it works, like, whenever I pick up another paper and someone has their own presentation of the DAHA, and I'm like, how do I write my intertwiners? If I just put down the commutator, it's going to work. Okay? By what I mean by that, you know, if you put it in PVW order, having, say, the y's to the right, then it'll be TYI minus YI plus 1 plus little t minus T inverse YI plus 1. And if you memorize intertwiners as looking like this, you're going to be in trouble when you go to some other presentation. Go to there, you'll be fine. And so you know, you might want to divide everything by YI plus 1, so you don't have this YI plus 1 there. And you might even also want to divide by T minus T inverse, because T is not a root of unity, so that you have an actual 1 there. What you kind of really want to do, though, to know that you're going to have a basis here, it would be nice if the p's were triangular with the t's. In other words, you'd like to divide by yi minus yi plus 1, but that's not a Laurent polynomial. You'd have to go to some localization to do that. And that localization is a lot like the one we saw in Jose's talk, going to differential operators by being able to divide by those alpha s's, right? And so let's not do that, although some people do. Okay, let's not do that because it's not legal. Let's not localize. Okay, but let's observe. So as long as yi minus yi plus 1 doesn't vanish on any weight vector, okay, let me call it weight vector u, then the span of u and TIU is equal to the span of u and CIU, and in particular two-dimensional. Okay, because this is going to be some non-zero scalar, so then you can divide by it. So you can't divide by the polynomial yi minus yi plus 1, but you can certainly divide by the constant that it acts by on a representation. And that's what you really want to do. So when you're building this basis, a good thing to do might be, divide by the appropriate constant here that is the value of yi minus yi plus 1. So I do get a leading term that's a t0 plus lower stuff to easily go back and forth between the bases to make a uni-upper triangular change of basis matrix. But I'm too lazy to do that. I'm just going to leave the constants in there and note that everything's okay. All right. But is everything okay? Do we have this non-vanishing? Absolutely, because I left up here what kind of weights that we have. And our genericity conditions on T and Q, these guys are never ever the same as each other. You can only have it happen if Q is some semi-power of T, or you get root unity or something. Okay. So that's great. Okay. And I should say that something that we ran out of time for, a calculation just in the affine Hecke algebra, just for H2, basically tells you that this condition, avoiding neighboring y's acting the same, is the key to the y's acting semi-simply, and the keys to having one-dimensional y weight spaces. And so that's a nice thing that you can show. And then one-dimensional weight spaces, that's where combinatorics comes in. That just really means you can be purely combinatorial. You can write wonderful things down. So let me write something down on the side. When you're able to avoid, let me say, make it this way. When you're able to achieve this non-vanishing, you get sort of y semi-simplicity of, well, you have to start out with irreducible representations. And this y semi-simplicity or x semi-simplicity, our room calls it calibrated, so there's papers that say calibrated are all about that. And you also get one-dimensional weight spaces for free. Okay, so totally different from what happens in Lie algebra with a carton acting semi-simply. You get high-dimensional weight spaces. That doesn't happen here. Okay, so it's beautiful combinatorics then. In the situation when you have y semi-simple irreducible, so automatically one-dimensional weight spaces, you can say, what's the combinatorial structure of those weight spaces, right? So in this packet it would be, only pick out the minimalized coset representatives and only those. There's a beautiful combinatorial structure in it that's very much like standard Young tableau, but they're periodic. They're periodic because how we have the y's wrapping around by the q's as you move between the integers and not just 1 through n. And that puts a periodicity, and you can write a periodic Young tableau, periodic diagrams, and that's some work that Cherednik has done, and I've done with Suzuki a lot of the combinatorics of that if you want to read more. And I wish I had more time to do it more explicitly, but you can read that on your own. All right. And another thing So what about the quadratic relation, right? I said, oh, we have these intertwiners, right? They have this leading term that's like a TI. It acts like the semi-direct product with maybe with the symmetric group on polynomials. Maybe it really is the symmetric group or affine symmetric group of polynomials. Well, we have to look at the quadratic relation, right? If we want to think of this as a quotient of the braid group, what's our quadratic relation? So the quadratic relation on the phis is phi squared is tyi minus t inverse yi plus 1 times 2yi plus 1 minus t inverse yi. Okay, so notice that what you get is symmetric under the action of SI, so it's in the fixed point of the SI action. And this works even when I is 0. Just use the trick to figure out what you get. Okay? And so what that means is that now if we're acting on weight vectors, what does that mean? That means that phi acts invertibly on a weight vector u of, let's say, that weight, I call it b1 up through bn, as long as two neighbors, bi over bi plus 1, that quotient, avoids, well, not just t squared, maybe also t to the minus 2. We can have something sign-like versus trivial-like. And remember, this was the condition that I was avoiding, that I wasn't allowed to cross starting from my trivial representation, and in fact, everywhere. Okay? So I'm not allowed to, so in other words, not only, do I still have them? Ah, they're erased. Okay. So as we were moving around these q to the somethings, t to the somethings, you could move them or move them back by an invertible operator. Okay? The only time you're not allowed to move something is like a 1 and a t squared, a t squared and a t to the 4th. Or maybe it could be a qt squared and a qt to the 4th. Those swaps you're not allowed to do. But any other swaps as you're building up these y weights, you're allowed to do. And it turns out that when you take our starting data and our minimum length coset representatives, you see that everything that you build up, all of these kind of edges between them, they are all invertible. Like all the swaps that you ever do avoid this. So let me just say, so the upshot, if we look at the y character of the polynomial representation, so then you do have to be careful and check only taking the minimum length coset representatives and which actual q to the somethings, t to the somethings we get. You can actually see that the polynomial representation is irreducible. In other words, take a submodule. Suppose you had a proper submodule. It has to have a y weight vector in it. Look at that weight. There's some permutation in affine Sn that gets me back to my 1 t squared t to the 4th. We'll act by appropriate phis, intertwiners, to get there. And they're always acting invertibly, meaning that guy, there's an operator from the DAHA that acts and never kills anything, gets you a non-zero scalar of your original 1 times 1, which generates the whole module, so it has to be irreducible. So we just proved that for q and t generic, it's irreducible. You said, I have till 10 till, you said?
What
Yeah.
assumptions are we making?
What assumptions are we making on the field? For all of this to work, we just need to have q and t be generic in the field. Yeah. Yeah.
And this quadratic relation, is that,
Yeah.
does that hold in the representation or in the DAHA?
No, this holds in the DAHA. There's
So
no
there's-
tensor 1 sitting there.
So there's no
In the DAHA.
no capital T's on the right.
Correct. It's in, not only is it in y, yeah. So part of being, sorry, I should have made a more point about this. It's not just in things that are fixed under SI action, it's in y. There's no capital T's at all. So it becomes all about the y spectrum. Right, and again, as long as you avoid, right, as long as you avoid that vanishing, the intertwiners do everything you need. And you can, yeah. So, should I write out that argument about why representation is irreducible? Did we follow it? Don't need to write it out. Okay. You can rewatch the tape for it. So, right. But another nice thing that holds, and this isn't just for Paul, this holds in general for representation theory. So let me call this condition double star. So let M be some simple DAHA module. That's Y locally finite. If double star holds, that you always avoid neighbors acting the same, then Phi squared U being 0 implies that Phi U is also 0. Certainly the converse holds, but this also holds. So in other words, you're simple, right? And so you start with the weight vector, and you propagate by using CWs to get a whole bunch of other weight vectors. And the question is, can you get everything, and can you tell combinatorially which weights you get and which weights you don't do? When do you fall off the edge and get a 0? You can just by looking at the weight, because phi squared lives in y, and so we know how to calculate that. That's just some scalar acting on this. And so, in other words, this condition about avoiding the quotient being t squared or t to the minus 2 actually tells you when can you actually do that swap and get a new eigenvector versus fall off the edge and get something that's 0. And I should say, because this is true, if you start with the module that you don't know if it's simple or not, and you're having this property hold, it's actually telling you when you get something that gets pushed into a proper submodule. In other words, if you do have a weight where neighbors are acting as a quotient being t squared or t to the minus 2, and you say, okay, let me push it using my intertwiner, that means you pushed it into a proper sub. Because if you were living in the quotient, which is simple, you would have gotten 0. Right? So modulo that proper sub being 0 means you landed in the proper sub. So this gives you a way of constructing proper sub, which, okay, I have I had a page out of order. I was like, where did it go? Okay, so I promised I would talk a little bit about a finite dimensional. How do you get finite dimensional representations? So let me draw for you the following picture. So let's take n equals 3. And I'm going to not be generic. I'm going to not take roots of unity, but I'm going to say q is t to the minus 3. Okay? Or what I really want to maybe think of it is that q squared is t to the minus 2 cubed is really kind of this pair 2, 3 matters more. And this has to do with how I presented the algebra, that there's this minus and this 2 there. So that's an artifact of the way I presented the algebra. So, all right, I'm going to draw the following picture and hope I can explain enough of what's going on. So, okay. All right, so I'm drawing a picture that goes with not the extended affine symmetric group, just plain affine symmetric group. So I could sort of put S0, S0, S1, S0, S2, S0, S1, S2, S0, S2, S1, S0, S1, S2, S1, and so on. These are going to mark my phi's, but there's a right, left, right something going on. Squared t to the 4th. Right? Act on it by phi 0. Right? And we stated that q inverse. Right? Act on it here and so on and so forth and see what you get. If I do this specialization, what does this become? It becomes t squared, t cubed. Put here phi 2, phi 0, tensor 1. Then we've got t cubed, t squared. S1, t squared, t cubed. Okay? Going from here to here, you're wanting to act by an S1 that wants to swap a t and a t cubed. What's the quotient of t and t cubed? It's a t plus or minus 2. So that means that when I cross this wall on this side, acting by phi 1, it says phi 1 squared. Right? This says that phi 1 squared, phi 2, phi 0, tensor 1 is 0. Okay, this specialization, well, okay, you have to worry about whether it violates genericity and such. But I say, that's telling me that actually the something that sits inside of here is going to be in a proper sub. This invertibility argument that says, oh, start with the weight vector of this weight, find the permutation that works me back here and work back, and you can do it, and you have your triangularity and non-vanishing and da-da-da-da. Nope, you get stuck in a proper sub here. Same thing here. You would want to swap these two. The quotient is a t squared. That means that, yes, you can move out with a phi 2, but you can't move backwards. This thing lands in a proper sub. Okay? And so, does that mean that when I quotient out by this proper sub, I get a 1, 2, 3, 4-dimensional representation? No, because I didn't write pi in this picture. Right? There's another sheet here that starts with pi and then moves on pi, s naught, pi, etc. Okay? But if we were in SL, not GL, these pi's would disappear, and this would essentially describe a 4-dimensional representation for the DAHA that you would put with SL when you make all your changes in the right way. And it's easy, once you've done all the work and understood your intertwiners, to convince yourself you really do get a proper sub here, and this is all that survives in the quotient. And then the combinatorics of the y weights of it are also easy and nice and combinatorial and beautiful. And some of the combinatorics that goes into here, you'll hear the words QT Catalan numbers, or parking functions, the statistics that you might see in here have to do with things like area and din, and so on. And then, and then one more thing, which is, I ran out of time. I worked out an example of actually writing these out in presentation 2. So getting actual x1s and x2s and x3s in here and writing it out, and those would be, you know, your nonsymmetric Macdonald polynomials up to rescaling. And if you write out what these intertwiners actually are and what they do, you could imagine this recursive formula for building up those polynomials and saying what's the coefficient of each monomial. And that's what, like, Knopf-Sahi did for Jack polynomials. And I think it's Heyman, Hagelin, Laurent, LRU that did it when it came to doing it for the non-symmetric Macdonald polynomials. I don't have time to write it out, but I'm happy to show you later if you want to see it. Okay, sorry to go over.
Are there any questions?
What's the sub-algebra DAHA generated by the intertwiners and
Oh, that's an interesting question. What is the sub-algebra that they generate?
I
It's,
don't
Sure it is, because we know the quadratic relation and the braid relations, and so you don't get TIs by themselves. You only get TIs with some extra polynomials and stuff in there. Oh yeah. Wait. Yeah. Oh, but if you have all, yeah, I think it's proper because you can't get rid of having the TI times YI. You can't cancel that out. With my yeah. What I don't know the other description of it, or it's something in there. If you localize and got rid of those denominators, then the localized things would agree. You would get the whole thing. But I think if you don't localize, it's some proper something.
So I'm just wondering. So you said the finite Hecke algebra is somehow deformation of the braid group of a disk, and then the AHA is for an analogous, and
well, you get as a quotient of it.
And the DAHA is for the punctors. Now the finite Hecke algebra somehow corresponds to Humphrey, and has this nice quotient which is temporally leap, which corresponds to Jones. So is there? Can you complete this picture? Is there somehow an analog of AHA but for temporally leap?
Well, there is an affine temporally leap algebra.
And then an analog of DAHA.
A double affine temporally leap.
One way to answer that would be that if you want to get Jones from Humphrey, you have to specialize the Q and T to be, T is an nth root of Q or something, right?
Yes.
So if you do this for the DAHA, then the algebra has lots of quotients, and so you get some more interesting representations.
Has somebody done something? Has done this?
Yeah, for instance,
Sorry?
yeah, people. He's asking about how does the representation theory change if T is an nth root of Q or Q is an nth root of T.
Oh.
That's a big,
Yeah.
the big story,
That's-
both for DAHA and for RCA. I mean, dozens, if not more.
But looking at sort of a quotient of that algebra and trying to get some of this temporally leabish, I haven't looked at.
Sure. But studying the representation theory in those cases. There's a lot of special combinatorics that happen there.
But yeah, I mean, you might also be able to do it more skeiny and more satisfying way as well.
Yeah, I would be interested to see some methods. Anyway, later maybe.
Yeah, but that's true. In a sense, that's what more people do.
Okay.
He's asking about skein algebra on the torus and relations
Yes.
to DAHA and what parameters, and it's the same instance of parameters.
Okay. I guess somehow when I think temporally leabish, I want pictures of things not crossing, but you're sort of saying, no, let them put the relations in and that will take care of it. Okay, sure. We'll talk more after.
Okay, any other questions? First thing one again. There's a group photo outside by the stairs. Is that correct?
The stairs by the elevator shows them how to take a photo looking down.
And for lunch, there's a nice park that they can direct you to.
Yeah, so the lunch today is like sandwiches. If you want, it's a sunny day outside, relatively. So if you wish, when you exit the building, if you turn right and you walk, then you turn. And then when you look to your left, you'll see some trees, and that's a university park that you can sit in the sun and eat your sandwich if you wish.
Can I suggest we thank all the speakers again?
And I would love to thank the organizers for putting together an amazing school. It's been a great week.
Let's go take a photo. Thank you.
Yes. Yes.
I mean,